Today we're going to continue with 9.3, and we're also going to start to look at 9.4, so we're going to look at ways in which we can use trig identities. We're also going to learn about a reference angle, how to find one, and be able to evaluate trig functions of any angle. So this is one use of trig identities. We're just going to briefly touch on it here in this chapter. We'll cover it a lot more in our next chapter. It is my favorite part of trig. So if you could see me now, you would see that I'm very giddy. But it's basically like doing a proof, except you don't need to explain your steps as long as they make sense. So what we're going to do is we're going to use trig identities to transfer one side of the equation into the other. There are many ways on a lot of these problems in which you can go about doing this. Some are going to be more efficient than others. So basically I have this equation here. I'm trying to prove that it is an equation. So the first thing I need to do is I need to pick one side and only work with that one side. Most of the time you want to pick what looks like the more complicated side. Now I know that seems a little bit counterintuitive, but it actually makes the problem easier. Then you're going to use your identities to substitute in, and you're going to use some basic algebra to prove that the one side does actually equal the other side. So here, if I look at this example, I'll kind of talk you through my thought process. So again, there are many ways in which you can approach this, and as long as you get the correct answer in the end, it doesn't matter. But you want to make it kind of as simple as yourself as possible. So I have cosecant of theta, tangent of theta, and secant of theta. So I'm thinking about my identities in my head. None of the identities directly relate cosecant with tangent, and then I'm trying to get a secant on this side. So, I'm trying to convert the left side into secant. So they do both relate to sines and cosines, or at least sine. So that's what I'm going to do first. So I'm going to change cosecant of theta into 1 over sine theta, and I'm going to change tangent of theta into sine of theta over cosine of theta. And I'm just leaving this as secant, so I'm just writing the equal sign. Now, using a little bit of algebra, I know the signs are going to cancel, and I know I'm left with 1 over cosine of theta, and so then my last step is to say this is secant of theta equals secant of theta. So again, this one is a very simple example. The ones we're going to do in this unit are fairly simple. They will become more complex in the next chapter, but this is such a fun thing that we want to at least get a taste of it now. So I want you to use your trig identities and prove that this is a true equation. So pause the video and go through that proof, and then unpause it when you're done. Okay, so here I have cosecants and cotangents on the left-hand side, and I have a 1 on the right-hand side. I have a product, and I can see I have addition and subtraction. So the first thing I'm going to do is multiply that out. My thought process there is I know that 1 deals with the Pythagorean identities, and the Pythagorean identities include squared terms. So I know if I multiply this out, I'm going to get something squared, and conveniently it becomes cosecant squared theta minus cotangent squared theta equals 1. So now I substitute it in. I know cosecant squared of theta is 1 plus cotangent squared of theta. The cotangent squared theta minus cotangent squared theta cancels, and I'm left with 1 equals 1. Now, just to show you, because I know you guys are going to start to jump to shortcuts, if I know this Pythagorean identity, I can rearrange any of these identities however I want. So I know if this is true, this has to be true. So I could have gone right from the green to my answer of 1 equals 1. But before you start taking shortcuts, you need to make sure you're proving to me that you understand why that works. Okay, let's try another one. So here you have the tangent of theta plus cotangent theta over tangent theta equals cosecant squared theta. So I want you to prove to me that this equation is true using your identities and basic algebra. Pause it, and then unpause it when you're ready to check your answer. Okay, so you might have done something slightly different, but what I chose to do is first split up the fraction on the left-hand side. So since they have a common denominator of tangent, I can make this tangent of theta over tangent of theta plus cotangent of theta over tangent of theta. Well, tangent over tangent is 1, cotangent over tangent is cotangent squared. If you're confused on how I got that, I did a little bit of work off to the side. You would not need to show this, but I know cotangent of theta over tangent of theta is the same as cotangent of theta times 1 over tangent of theta, but 1 over tangent of theta is cotangent of theta. So that's how I got the cotangent squared. And then from my Pythagorean identity, 1 plus cotangent squared theta is cosecant squared theta. So there, I'm done with my proof. One thing to point out about these problems, it will work out. I'm not going to try to trick you. I mean, sometimes I do try to trick you, but now it's something like this. So if you're not getting it, it's not because it doesn't work, unless I gave you a bad problem. But I'm not going to intentionally do that. Okay, now we're going to define a few things. Reference angle. This is going to be an incredibly important term. We've actually used the idea of a reference angle already, but we just didn't define it. So our definition is, let theta be an angle in standard position its reference angle is the acute angle theta prime, so that's what this is, theta prime, formed by the terminal side of theta and the horizontal axis. So what does that mean? Well, I'll draw you a few pictures. One, it means if theta is in the first quadrant, then theta is also its own reference angle, assuming that it's not greater than 360 or less than 360 and so on. But for instance, so this will make more sense hopefully. If I have some angle here, and this is theta, then this angle here is theta prime. Let's do another one. So if I'm in, let's say, the third quadrant, so this is theta, then this is theta prime. If I'm in the fourth quadrant, this is theta, then this is theta prime. The reference angle is always positive because it's an acute angle. I'll take back what I said earlier. If I have, let's say, in the first quadrant, if I have this angle, then this is theta prime. So the red is theta. So those are examples of reference angles. So it's always going to relate to 180 or 360 or pi or 2 pi somehow. So then the quadrant angle. So this is defined as an angle with a terminal side that lies on an axis. So, for example, 90 degrees, pi, 4 pi, those would all be examples of quadrant angles. Okay, let's go back to the reference angle, because again, this is an incredibly important concept. So I want you to find the reference angle of all of these angles here. And remember, if it's not specified as degrees, then you assume that it's radians. So here I have 217 degrees. So what is the reference angle? So if this is theta, then I know, well, where is 217 degrees? Well, 217 degrees is going to be in the third quadrant, so I'm trying to find this angle right here. Well, how can I find that? I can subtract from 180. So what is 217 minus 180? That's going to be 37 degrees. So my reference angle is 37 degrees. So I want you to use that concept and find the reference angle for the remaining angles here. If it's in radians, have your reference angle in radians. If the original is in degrees, have your reference angle in degrees. Pause the video, unpause it when you have your answers and want to check. Okay, so here you can check your answers, and you can see I tried to draw a picture for some of these to help you out if you were confused. So for instance, if theta is 5 pi fourths, then theta prime is going to be pi fourths. So here in the red is 5 pi fourths. This angle here has to be pi fourths. Relates to pi. Let's look at this one. Theta is 170 degrees. Theta prime is going to be 10 degrees. So here is 170. What's left over to get me to that horizontal axis? That's going to be 10 degrees. Here, this one was a little tricky maybe. So if theta is negative 17 pi fifths, well, where is that? That's in the second quadrant. So if I go around, this is negative 5 pi fifths, negative 10 pi fifths, negative 15 pi fifths, and then up here is negative 17 pi fifths. So this angle here is going to be the reference angle, and that was 2 pi fifths. I didn't draw a picture for this one because I was hoping it was pretty straightforward. If theta is negative 27 degrees, the reference angle is 27 degrees. If theta is 1 radian, the reference angle is also 1 radian. 1 radian is a positive acute angle. Okay, next thing we're going to look at are what's called trigonometric functions of any angle. So far we've been dealing with the unit circle, so we had a radius of 1. Well, what if we don't have a radius of 1? Well, everything still works the same. So let theta be an angle in standard position with xy, a point on the terminal side of theta, and r is the square root of x squared plus y squared, which does not equal 0. So if this is the case, and then I know sine of theta equals y over r. And now just to point out, so this is the exact same thing as what we've been doing, it's just with the unit circle, r was 1. So that's why we said sine of theta equaled y. So then going through the rest of these, I can see that cosine of theta is x over r, tangent of theta is y over x cannot equal 0. Cosecant of theta is r over y when y does not equal 0. Secant of theta is r over x when x does not equal 0. And cotangent of theta is x over y when y does not equal 0. And where this comes from is if I draw this picture here. So this is just an example where if this is my angle theta, this is the length r, and this is the point xy. And this could be in any quadrant. This is just the example that I drew. So we have a few examples we want to do with this, but we're running out of time for this one, so that'll be in part 2.